apply this or to think about it, it's hard to think about motion like this where it's not just simple projectile motion where your acceleration is constant here. Before you looked at the fact that the derivatives don't just come down to be a constant. Sorry, where were we here? Right here. The derivatives don't just boil down to a constant and then zero like they do with power functions. For projectiles, if you start with something that's a quadratic, after a couple you come up with constant, the acceleration's constant. If we start in anywhere in this list with the original function involving one of these trig functions, the acceleration's not going to be constant. None of the derivatives are. So that's what looking at this is here. I personally have a hard time wrapping my head around this and have to think about it every single time it comes up. But think about as this is moving here. So 5 cos t, where is it starting here? Let's first, 5 cos t, what's its position at the beginning here? At 5, right? So if you had a graph of the position, this is S, it starts at 5. Okay? I don't know why these are minus on top here, but 5 cos t means it starts at the top, right? And it's going like this. So I'm thinking that if this is where it's starting, this should be positive 5 up here, and this. Okay, yeah. Well, they got the arrow going the right way, anyways, pointing towards the positives. No, but the first picture has it at the top, is what I'm thinking. Anyway, so whichever way you define the axes, it's starting at positive 5, wherever that is. And it's going down and up and down and up. Think about what the velocity represents here. We'll do velocity and then we'll see if we can handle the other stuff. What's the velocity of this going to look like? Okay, we'll reenact it here. It's starting at the top at 5. It's not moving when it starts. It falls quickly and then it stops. And then it rises up here, it stops. And then it goes down here and it stops. And then it moves up here and it stops. And it keeps doing that, right? How does that represent its velocity graph here? What's the derivative at the beginning here? The derivative's 0 at the beginning. This is 0, that's when I'm holding it at the top, right? Its derivative 0 at the beginning. Yeah, then it gets faster. In the which direction here? Negative, because the way I defined it, that's going in the negative direction, right? Because I changed this so that up was positive here, right? So it's got a negative velocity here, so it's going to go down here, and it's going to come back up. I don't know if my points are going to match here, but something like that. This is where it's 0 again. So this is 0. This is where it's 0 again. And my graph is not drawn very well, but it should be the graph of what? Negative sine x, right? The velocity is negative 5, negative 5 sine t. That's how the speed is behaving. It's going fastest when it's passing through the middle. Okay? When it's passing through the middle, that's when it's going fastest. It's going fastest in the negative direction there. It's going fastest in the positive direction through the middle there. How about if we describe the acceleration now? I don't have much room for this, but we'll put it down below here, I guess. Do a little acceleration graph right here. What does the acceleration look like? I guess we could write out the function first and then think about it. How is its speed changing? Look at the slope of this graph. The slope of this graph is the second derivative. The slope of the first derivative is the second derivative. So if you're trying to graph it, here's where the slope is 0 there, right? So at this point it's 0. At this beginning point here, what's the slope of that? Negative 5, I guess, because it's expanded, so down there. At this point, it's that maximum value. And then here it's 0 again. And then it's minimum value. What's that the graph of? Yeah, this is negative 5 cos t. At the beginning, the way that the velocity is changing is at its most negative, right? It's hard to comprehend acceleration that is changing because a lot of what you've looked at is acceleration that's constant. You launch a ball up in the air, the acceleration is constant. Here the acceleration is changing as it goes. When it's at the top, what's happening with its speed? It's being accelerated, like the speed is becoming more, well, it's at the top, the speed is starting at 0, but it's becoming more negative right after I let it go, right? It's 0 speed at the beginning, and it's becoming more negative after I drop it. Up to this point, right? It's becoming more negative up to the middle. It's getting faster in the downward direction. What happens after it passes the middle point, though? It's slowing down, so that's why that velocity graph's turning around. Now its speed is changing the other direction. As soon as it hits the middle point, then its speed is changing in the other direction. That's where its acceleration changes. Till it hits that middle point, that acceleration is negative. As soon as it passes the middle point, its acceleration is positive because the velocity is changing the other direction. And then once it gets to this point, at the very bottom, that's where its acceleration is the most positive, because what's the spring doing to it? At the bottom, what's the spring doing to it? It's pulling it upward, right? That's where it's got its maximum acceleration, right? This point right here. After that, as the spring pulls it up, what's happening to its acceleration? It's decreasing. It's still positive up to this point, but after it passes the middle point, again here, okay, after it passes that middle point, what happens to the acceleration? It's negative because now we also have the other effect, like it's the spring, but it's also gravity, right? So after you pass this middle point here, the spring's not doing a whole lot anymore and gravity's doing more, right? So then its acceleration becomes negative again. That is a difficult concept to think about acceleration that changes as the motion happens. And then, let alone talk about the rate of change of acceleration. This is the rate of change of acceleration. So I think at this point, take a minute to try and think through that situation and how that's changing. Comment or question?
Shouldn't the acceleration be 0 when it's, or start to be negative when it starts to go back? It should be the maximum when it's accelerating that way the fastest, and when it slow down to 0, then it'll go negative as it starts to be pulled back, not when it crosses the displacement point. What? Please keep thinking that over.
Here's where the acceleration changes from positive to negative. The speed changes from positive to negative at what point here? I'm recording this? I recorded that. Okay, think about where the acceleration changes. The acceleration changes at these points, right? For the beginning, the acceleration is negative. This is where it changes. The acceleration changes to positive. If you want to think about it this way, when the spring is really stretched out, what's winning, the spring or gravity? The spring, right? When it's up here, what's winning? Gravity, right? As soon as it passes that midpoint, that's where one takes over from the other. That's where the acceleration changes here. Okay? The acceleration is how it's affecting the speed of the thing. The speed changes when the thing is at the top or the bottom, right? The speed changes, you can see the speed changing, right? When it's moving up, the speed's positive. When it's moving down, the speed's negative. The speed starts out up here at 0. It's negative for the entire trip down. Yeah, sorry. Velocity. Very good point. Good point. Yeah, that's very good. The acceleration changes in the middle. It has to do with the spring and with gravity. Okay? If you graph the jerk involved here, yeah, I can never say that without thinking it's so silly, but if you draw a graph of the jerk here, 10 minutes, okay.
10 minutes.
Thank you. We'll have to, yeah, then we can